So here we are, week 26, learning about light. So two terms, luminous and illuminated. So a source of light that is luminous is a source that produces light. And I'll give you an example here soon. Source that produces light. And when something is illuminated, this is a source that reflects. How do I spell reflects? There. Reflects light, but does not produce it. So, hold on, we're both writing. Alright, so an illuminated source reflects but does not produce it. So here are two examples. A luminous source would be our friend, the sun. So the sun actually produces light, and here's our sun, and our life on Earth depends on that. Okay, and an illuminated source would be the moon. So we look into the sky and we see the moon, and the moon is shining bright. The moon itself is just a chunk of rock. It doesn't actually produce light. What happens is light from the sun, this is not drawn to scale or anything, light from the sun hits the moon and reflects towards us. So we see the moon at night because the sun would be behind us and the moon is in front of us. And we get to talk more about that later as well. So, two classic examples of illuminated and luminous sources. Okay, so lightning strikes. We live here in the Sierras, and we've all seen lightning and unfortunately been pretty close to it. So, you know, I've had the situation, dude, how close is that lightning to us, right? We see the lightning flash and then we hear the thunder. So what happens is we know that the speed of light is very fast, 3 times 10 to the 8th meters per second. And we know that the speed of sound is, well, still fast compared to how fast we could run or something, but very slow compared to light, 343 meters per second. So you have probably done that thing where you count. So if you count, so this person's going to give some instructions. Count seconds, and 5 seconds equals 1 mile. What on earth does that mean? So the reality is that the light gets to you basically instantaneously. If you're in the same mountain range as the lightning, the amount of time it takes is going to be something very, very, very small, like, I don't know, that seconds. So it's basically nothing. Sound, however, only travels this far, and so if you were to calculate distance equals velocity times time and plug in speed of sound and then the distance of 1 mile, you would get that t, so time is about 5 seconds per mile. So anyway, next time you're in a lightning storm or near one, once you see the flash of lightning, count, and every 5 seconds that it takes until the thunder gets to you, that means that it is that far away. Okay, 3 other terms. Reflection, which you've definitely heard. You see your reflection in the mirror. Refraction and diffraction. So I have some examples on the subsequent pages. Let me just write definitions here. So reflection is waves bounce off a surface. Okay, sounds reasonable. Refraction is what happens when waves bend as they pass from one medium into another. So waves bend as they pass from one medium into another. And diffraction is waves bend around corners. So I have a bunch of sort of images and diagrams on the next pages, and when I show you those, why don't you go ahead and draw some diagrams in here, at least one diagram for each of these. All right. So here we have, let's get these guys out of the way. So here we have, this is diffraction. So if you've ever been to a harbor or something where boats are stored, right? So this is land, and this out here is the ocean, and these are wave fronts. So these might be the crests of the waves. And there will be, in a lot of harbors, there are these sort of man-made, these big rocks, like a jetty, that basically block a lot of the waves. And there's some little opening so the boats can come in and out. But because the opening is little, not much energy from the waves is actually transmitted through. But look at what happens. It's not just this, right? This thin little column of waves that comes through like that. No, no, no. Oh, I guess I can't erase. Let's see. There we go. So what happens is we have these corners. So there's a corner right here, and there's a corner right here. And when this wave gets here, it actually sort of spreads out from that corner. And so we get these wave fronts. So they're bending as they pass through this little opening. So this is an example of diffraction. Waves bend around corners. And this is similar. So we have waves coming in, there's a little opening, and they spread out like this. These arrows are just indicating the direction of the waves. The wave fronts would look like this. Okay, diffraction. Ask me in class to show you an example of diffraction, and I have one that's pretty fun. Okay, so here's reflection, where we have a reflecting surface, so the mirror, and there could be some flashlight, and notice how it bounces off at the same angle, basically. And I think that's going to be intuitive to you. Those angles are the same. In physics, we say the angle of incidence equals the angle of reflection. This is the normal, or perpendicular to the surface, but I think that's pretty straightforward. Next step, so refraction. This, in my opinion, is the coolest. So you've probably seen something like this, and it's not, the pen is not broken. All right, what's happening is light from this region of the pen is just passing straight to our eye. Region from this end of the pen has to pass through this acrylic block, and so it actually kind of does a little bending. So let's see. Here's the acrylic block, and here is the light wave. It's going to do something like that. So instead of the original one, right, going in this direction, the bent light wave is in this direction. So it's in the same, they're parallel, it's in the same direction. We see the same pen, but notice how it's offset a little bit. So we see this offset like that. So this is an example of refraction, right? The light wave bends as it passes from one medium into another, and then as it passes back out into air, it's now parallel to the light wave in air. If you have, you can look at the fish tank in the library, and you'll see something like this. So it turns out that the image that we see of the fish, they look closer to the surface than they actually are. They also look bigger. I remember going scuba diving, and we caught this fish, and I was like, "That fish is huge!" And I thought we were all victorious, and we got out, and the poor little fish was just this little guy. Oh well, I didn't know much about refraction at that point. So, all right, Pink Floyd album cover, another example of refraction. So we have white light coming into a prism, and it bends a little bit, and then it bends a little bit more, and it turns out that different frequencies, so different colors have different frequencies, right? They actually bend at different amounts. So the higher frequency purple bends a little bit more. The lower frequency red bends a little bit less. So a prism that doesn't have parallel sides can actually separate white light into its component colors. Yes, we have one of these. Notice how this, because it's parallel sided, it didn't separate it out into any cool rainbow or anything. Okay, another example of refraction. Ray diagrams. Hey, ray diagrams. We will be doing these for different types of lenses and stuff, but here's some creepy looking guy, and he's looking in a mirror. So here's a mirror. All right, and you can forget about him for a little bit, but this is actually what this person sees. So you look in the mirror and you see a reflection. That's pretty basic, right? But here's what's actually happening. You see yourself because light from the just the room or the window or whatever bounces off you. So hey, so here's some light and it bounces off his hair and it bounces off the mirror and gets to his eyes. And his eyes say, oh, there's my hair. And so his eyes interpret that signal as having come from over here. And light from the room bounces off his shoes and bounces off the mirror and hits his eyes, and his eyes say, oh, there are my shoes. And his eyes interpret that signal as having come from here. So this is what our brain processes from all the light that bounces off us, off the mirror, and back to our eyes. And we see ourselves over here. So the interesting thing, in my opinion, is that in order to see, so this guy right here, Joey, oops, hey, sorry, Joey. Let me erase that. So this guy here is seeing his entire reflection, yet the amount of the mirror that he's actually using is this. So the distance between his eyes and the top of his head is cut in half, and the distance between his eyes and his feet is cut in half. So this mirror is actually only half of his exact height, yet he can see his entire reflection in it. And so the other question is, well, how far away? So if he's, let's say he's standing 3 feet from the mirror, his image actually looks 6 feet away. So that's a 6 ft. So that's that may be a little counterintuitive, but next time you see a full-length mirror, you're going to check it out and go, whoa, that is correct. All right, so that's our intro to ray diagrams. I think that you can answer these questions, because I think I just did, so you should answer them. And lastly, we're going to get into talking about lenses. We have a bunch of lenses that we get to experiment with. And if you ride a skateboard, you know this is concave. That's how I remember it. If you don't, well, this is concave lens and this is convex. So when it bulges out in the middle is convex and bulges in is concave. A magnifying glass is a convex lens. So if we were looking at it from the side, it would be like this. And what happens, you may have had the, you focus the light and it burns your hand or something like that. So light from the sun comes in parallel, and what this does is it focuses it, so it will actually have a focal point. And all of those light rays that came in parallel focus onto one particular point. So it's all this light energy that's focused at one tiny little point. So if you put your hand under it, just, I wonder what this is like. Ouch, that's going to hurt. So you can burn yourself. I don't recommend it. But anyway, that's what a magnifying glass does. So we are going to talk about these concave and convex lenses. The concave lenses actually end up dispersing the light, so spreading it out, whereas the concave lenses end up focusing it like this. Okay, so a lot more about that later, and that's our intro.